for any x, there will be a corresponding fiber equivalence class x bar, so that theta of this, which is that, maps to y. So every y, for each y, there is an equivalence class, a fiber that is mapped from into y. So for each y, there's a fiber that you use to map into y, right? So therefore, this function phi is surjective. Okay, so it's injective and surjective, therefore it's bijective. So you can map bijectively a fiber, yes, the set of elements of x here that are all equivalent to each other. So you can map that whole band or fiber into that one point. So it's a very much a many-to-one mapping. But the fiber maps one-to-one. Okay, you appreciate the distinction? The fiber maps one-to-one into these points, these elements of the image of f. Okay, now let's actually do a few exercises. I could do this almost verbally. I could rub out. I'll get something to rub out quickly. The beauty of this new board is that it rubs out very easily. It's so superior because I guess the chemical coating is better. Maybe the previous one was a fake. A lot of that goes on in China. All right. Question 1, part 3. You've set as the integers. So a is just the integers, and two members of a, or two integers in other words, they are equivalent. Let's if x minus y is divisible by 2. So if x minus y, if the difference between them is divisible by 2, now you can rewrite that another way. That's the definition of x is congruent to y mod 2, right? So you have to show that this relation, equivalence relation, then you have to show this relation is an equivalence relation. So you have to go through those 3 steps. You have to show the relation is reflexive, symmetric, and what's the word? Forgetting. Yeah. All right. All right. So let's show now. Is it that? Is that valid? Does that work? Question mark. So is x congruent to x mod 2? So does 2 divide x minus x, which is 0? Does 2 divide 0? Yes, it does. So that's okay. So it is reflexive. Now, is it symmetric? So if x is so if x tilde y is y tilde x, is that true? So if x is congruent to y mod 2, y is congruent to x mod 2. You put it this way, like if x minus y is divisible by 2, then it's of this form, 2k, k is some integer, right? Well then y minus x will just be minus 2k, okay? And therefore this you can divide this by 2 because you can divide that by 2. So that's true. So this relation is symmetric. Transitive was the word I was trying to find before. All right, now is it transitive? So if x is x tilde y and y tilde z, how about x tilde z? Question mark. Is that true? Is it Is this relation transitive? Well, if x is congruent to y and y is congruent to z, then x is congruent to z. And that means that if x is congruent to z mod 2, then x minus z is divisible by 2. So that's true. So therefore all three are satisfied, all three conditions. Therefore this relation is what's the word? My memory seems to be an issue. I must be getting old. Maybe it's just a question of calories. But I've been eating. Alright, so in each case identify the equivalence classes. So what are the classes? So if you had, like the odd numbers, they are equivalent to each other. Like they would be of the form 2k plus 1 minus 2m plus 1. So your odds minus odds, that's still divisible. Yeah, the ones cancel. So it's the difference is still divisible by 2. So I guess the equivalence classes would be the even integers, the evens, and another equivalence class. Remember disjoint. That's one of the theorems. Are the odd numbers, the odd integers. So you have two equivalence classes: the even integers and the odd integers. Let's just check on that. So 1.3. Equivalence classes are the even and odd integers. All right. Now you'll see how easily I can rub this out. It's very nice. If you've been following these lectures from the beginning, you remember the trouble I used to have with the old board. Oh, that's gone, thank God. All right. Okay, 1.5. Your set is again the integers, and x is said to be congruent to y if mod x equals mod y. In other words, the absolute value of this integer is equal to the absolute value of this other integer. Okay. Well, so is x equivalent to x? So is mod x equal to mod x? Yes, obviously. So x is equivalent to x. So it is reflexive, right? This relation. Now, if mod x equals mod y, then mod y equals mod x, and therefore y is equivalent to x. Right? So it is symmetric. Now, how about transitive? If x is equivalent to y and y is equivalent to z, well, that means if this is true, then mod x equals mod y, and this is true, mod y equals mod z. Mod y is mod z. Mod z. Okay, so if mod x equals mod y and mod y equals mod z, therefore mod x equals mod z, and therefore x is equivalent to z. Right? So it is transitive, and all three conditions are satisfied. Therefore, this relation here is a congruence relation. Right? So what are the equivalence classes? What are the equivalence classes? Well, we're talking about mod. So what are the y's that give you the same value as that? Well, you could have plus or minus x, right? So it's the set of y's such that y is equal to plus or minus x. Right? That's, so each congruence class has two members, plus or minus the value of this one. Okay? So in other words, x bar is this. Okie dokie. Okay, now. So this time you have to, well, it's much the same. You decide whether it's an equivalence relation, and again find the equivalence classes if appropriate. All right. And again, it's on the integers. So your set is z. Two elements. X is said to be, x is congruent to y if x and y are greater than 0. Does that even make sense? I mean, this restriction here is making me suspicious. So maybe you can find a counterexample where that's not true. We have to get. We're trying to prove that this relation is a congruence relation. Sorry, equivalence relation. So we have to go through those 3 steps. So how about reflexive? Is x equivalent to is x equivalent to x? Well, that means you've got an x here, so you've got x squared, and so you've got to have x squared greater than 0. But look, my set is